Good day and welcome back to the second part of our discussion on partial derivatives. In the first video, we introduced kind of the concept of the partial derivative, and we viewed it from the computational perspective. In this video, we are going to really explore the geometric interpretation of the partial derivative. And to explain the interpretation, we have this generic representation of a surface. So thinking that we're starting off with a function of two variables, f of x, y, and graphically we can think of it as being z equals f of x, y, to give this surface sitting in three-dimensional space. And what we would like to do is come up with some interpretation of the quantity partial of f with respect to x at a point and the partial of f with respect to y at a point. How can we physically interpret those in terms of our picture? And we have a few kind of guidelines here. Sketch the y equals b trace and call it C1. So if I want to think of the y equals b trace, I take the y equals b plane and think about where it cuts my solids. And just for fun here, let's go ahead and throw that in. If we have the y equals b plane, we want to think, where does that kind of cut through our surface? I'm going to remove this from the picture just to make it look a bit nicer, but the trace is essentially a curve that looks something like this. And I'm going to call it C1 to give it a name. Similarly, we can form what we're going to call C2, which would be the x equals a trace. So the x equals a trace, we think where that x equals a plane cuts our surface, and it's going to cut the surface at some curve that looks roughly of the form here, and we call this C2. And now we can interpret both the partial with respect to x and the partial with respect to y at that point AB. If we look at the curve C1, the curve C1 has a tangent line to it in that y equals b plane. And the tangent line in that y equals b plane has slope determined by the partial derivative with respect to x. So this is a tangent line in the y equals b plane, or trace, and the slope of that tangent line is the partial derivative of f with respect to x at AB. So guess what? We still have a very similar interpretation of the derivative. It tells us something about the slope of a tangent line. Similarly, the curve C2 in that x equals a plane has a tangent line at that point ABC. And the tangent line in the x equals a plane has slope given now by the partial with respect to y at a comma b. So just to summarize, the partial derivative of f with respect to x at AB is the slope of the tangent line to the curve C1 at the point A, B, C. And just to make sure there's no confusion, C is the output associated with the input, AB. Similarly, the partial with respect to y is the tangent line to the curve C2 at that same point. And this physical interpretation is going to be important for us, as it's something that in our next section is going to come back up again. For now, though, let's go to a nice concrete example where we can visualize these interpretations. We are now going to finish up this discussion of the interpretation of the partial derivative by looking at a nice concrete example. For the function given by 16 minus 4x squared minus y squared, let's find and interpret the value given by the partial derivative with respect to x at the point 1, 2. And the first thing I want to do is just try to sketch the graph of this function of two variables. And note, z equals 16 minus 4x squared minus y squared is a familiar object. It's a paraboloid. Going back to our discussion on quadratic surfaces, we can note either from recognizing this, or I guess we could go through the method of traces, we're going to have a paraboloid that opens downward kind of along that z-axis. So if I was to just go ahead and sketch the portion of this paraboloid sitting in the first octant, roughly speaking, without trying to be overly accurate, it's going to look something roughly speaking like this. And by inspection, we can even read off what those positive intercepts are going to be. So if we want to think of that x-intercept, so we think something 0, 0, if y and z are both 0, x would have to be 2. Similarly, if x and z are both forced to be 0, that means y would have to be 4. And if x and y are both 0, z is left being exactly 16. And what we would like to do is find and interpret the partial derivative with respect to x at the point 1, 2. So I can see 1, 2 sitting right about here in the z equals 0 plane. So when we say 1, 2, it's really 1, 2, 0. And at 1, 2, 0, we can trace up to a point on our surface. And if x and y are 1 and 2 respectively, then our output is 8. So to the side here, I'll just note, so there's no confusion, f of 1, 2 is 16 minus 4 minus 4, which is 8. So before computationally determining the value of the partial derivative at 1, 2, let's interpret it. So to interpret this partial derivative, we look at the y equals 2 trace, because we want to fix y and vary in the x direction. And the y equals 2 trace would be where that y equals 2 plane cuts our surface. So in black, we have the y equals 2 trace. And the tangent line to this trace at the point 1, 2, 8 in the y equals 2 plane has a slope given by the partial with respect to x at that point 1, 2. And stated as simply as possible, we are fixing the value y equals 2, which puts us in the y equals 2 trace, and then we think about how we change if we let the x vary. In words, we can interpret the partial of f with respect to x at 1, 2 is the slope of the tangent line of the y equals 2 trace of our function f, and I'm going to be as specific as possible and write it down, at the point 1, 2, 8. And I really view this as being kind of the most difficult part of this problem, kind of physically or geometrically interpreting this derivative. So after we go through a quick computation, we'll come back to this visualization and we'll use GeoGebra to help us out a little bit. So note, computationally, f sub x is found by treating the y as a constant. So the derivative of a constant 16 is 0. The derivative of minus 4x squared with respect to x is minus 8x. And the derivative of that constant minus y squared is 0. Which gives us that the partial of f with respect to x at 1, 2 is minus 8. That is, as we go in the positive x direction, so think out of the screen towards you, the output is getting smaller. So the negative slope does in fact make sense. And to help visualize this scenario as well as we possibly can, I have a little video clip of a GeoGebra animation that I'm going to talk over. So what we are seeing is our surface is paraboloid opening downward, having a z-intercept of 16. We're interested in specifically this point 1, 2, 8. To get the partial derivative with respect to x, we think of the y equals 2 trace, which is the intersection of the surface with that y equals 2 plane. And furthermore, note that at that point 1, 2, 8, the partial derivative with respect to x is the slope of the tangent line. And hopefully this helps to just better illustrate that interpretation that we have of the partial derivative. In the next video, we will investigate some further examples, specifically things related to higher order partial derivatives and implicit differentiation. So stay tuned and take care.